a few moments to wait to make sure the live stream is working. This is going to be the Dining Philosophers medium LeetCode 1226. Make sure the live stream is working. I got audio, pop out the chat. Just keep going for a little while longer. Well, yeah, I can go till like a little bit later. I think I'm good to go here. Yeah, okay. Dining Philosophers. Okay, and I can close this one. This one is already refreshed. Okay, the Dining Philosophers, 5 silent philosophers sit at a round table with bowls of spaghetti. Forks are placed between each pair of adjacent philosophers. Each philosopher must alternately think and eat. However, a philosopher can only eat spaghetti when they have both left and right forks. Each fork can be held by only one philosopher, and so a philosopher can use the fork only if it is not being used by another philosopher. After an individual philosopher finishes eating, they need to put down both forks so that the forks become available to others. A philosopher can take the fork on their right or the one on their left as they become available, but cannot start eating before getting both forks. Eating is not limited by the remaining amounts of spaghetti or stomach space. An infinite supply and an infinite demand are assumed. Design a discipline of behavior, concurrent algorithms such that no philosopher will starve, i.e. each can forever continue to alternate between eating and thinking, assuming that no philosopher can know when others may want to eat or think. Oh no. Problem statement and the image above are taken from wikipedia.org. No kidding. Oh no. Talk about concurrency. Oh boy. Hoping for like an easy question. I was thinking about taking a break after this too. Oh boy. Kind of in a bad mood. Philosophers' IDs are numbered from 0 to 4 in a clockwise order. Implement the function void wants to eat. Excuse me. Philosopher, pick left fork, pick right fork, eat, put left fork, put right fork, where. Philosopher is the ID of the philosopher who wants to eat. Pick left fork and pick right fork are functions you can call to pick the corresponding forks of that philosopher. Eat is a function you can call to let the philosopher eat once he has picked both forks. Put left fork and put right fork are functions you can call to put down the corresponding forks of that philosopher. The philosophers are assumed to be thinking as long as they are not asking to eat. The function is not being called with their number. 5 threads, each representing a philosopher, will simultaneously use one object of your class to simulate the process. The function may be called for the same philosopher more than once, even before the last call ends. I forgot to use scoped locks for the last question that I was working on before. I think a scoped lock is better than just locking and unlocking a mutex. Ooh, excuse me. Scope locked object is created, attempts to take ownership of the mutex as it is given. When control leaves the scope in which the scope lock object was created, scope lock is destructed and the mutexes are released. If several mutexes are given, deadlock avoidance algorithm is used as if by standard lock. It's non-copyable. Actually, I think the application I was trying to use it for was not appropriate to try to use a scoped lock. Excuse me. Okay. Let's use lock guard, use unique locks, stop lock, defer lock, scope lock. Oh. Excuse me. Oh boy. Input n equals 1, output. Okay. N is the number of times each philosopher will call the function. The output array describes the calls you made to the functions, controlling the forks in the each function. Its format is output by ABC 3 integers. A is the ID of a philosopher. B specifies the fork, left, right. C specifies the operation, pick, put, eat. Excuse me, pretty low submission rate, relatively high acceptance rate. I don't know. I don't even know where to begin with this. No. What am I supposed to do? What are we doing? So some value of n, and then there's some output array. So I'm trying to make sure the philosophers don't starve. Excuse me. They're not asking to eat. So 5 threads use one object to simulate the process. Maybe call for the same philosopher more than once, even before the last call ends. Which function may be called? Their IDs are numbered 0 to 4 in clockwise order. 0, 1, 2, 3, 4. Implement the function wants to eat where excuse me. Oh, what is even happening here? I think I want to have a mutex for. Discipline of behavior, concurrent algorithm says that no philosopher will starve. Each can forever continue to alternate between eating and thinking, assuming that no philosopher can know when others may want to eat or drink or think. What is n though? What is n supposed to be? N is the number of times each philosopher will call the function. So when n equals 1, could do 4, 2, 1. What's 2? The fork. And then pick up, put down, eat. Where's 3? Okay, 4, 0, 3. All right. So what does my output look like if I just pick left, pick right, and eat? What is going on? I don't understand. I'm very confused. And I kind of just want to go to sleep. I mean, not sleep, but just... I'm not sure if I particularly care that much about this question. Alright, so this is a wrong answer. For some reason. Reasons that are unbeknownst to me. So 0, 1, 1. Oh, I see. These things happen concurrently. I see. Each philosopher is going to, okay. Alright, this happens concurrently, so I think I need to pick up the forks and put them down in sequence. Well, I mean, I could make things kind of complicated. Maybe I'll just have a mutex for each fork. Maybe that's how it works. Right. Not have a deadlock of some kind. Excuse me. Could also do it this way too, where they just, you know. Could do something like the following. Scope lock. Yeah. Adopt lock. Yeah, okay. Just scope lock, SLK. And then that's it. I think this works, quite frankly. I think this works. Doesn't work. Doesn't work the way that I've described it. Do I need to do anything here? I don't know if there's any particular thing I need to do with this. Yeah, that works. I mean, it's one way of doing things, right? Can I'm very tempted to just submit this one and move on. It's one way of doing things. Maybe not the best way of doing it, but it works. If it works, oh, great. Please tell me this works. I think it works. I could have tested all the cases. Oh, that's so much easier. Oh, what a relief. Not the most efficient way, I'm sure, but yeah, basically, you know, whoever's using the forks are just gonna do it one at a time. Really? That was easy. That wasn't too bad. Oh, that's hilarious. Gee, that's very funny. I basically just programmed it where only one person can eat at a time. It's ridiculous. Works. 1, 2, 3, 4. It's not very efficient, but you know, hey. I don't know. 1, 2, 3, 4, 5, 6. I don't know how. Excuse me. I don't know how it's supposed to be. I mean, it's, you know, it's good runtime. It's a good runtime. I don't know. Yeah, it's probably one of those things where it's like, I wonder if that's actually the solution I'm supposed to produce. It's like probably not the most efficient way to do it, but also like there's only 5 of them, and there's only 5 of them to begin with, and it's only like 1 to 60, so it's kind of like I don't know. It's just practice with concurrency primitives. Anyway, thank you for watching. I'm gonna go ahead and take a break, I think, for a few minutes. I don't know what I'm gonna do. I'm like kind of down, feeling down. I wanted to just make like 10 to get through 10 questions today. I just thought that would be cool to do. So thank you for watching. If you like this video, give it a like and subscribe for more. Yeah, I'm gonna take a break. I don't know if I'm gonna keep going later today. I might, maybe not.